Okay, thank you, Bhavesh. So let me begin. Okay, so we'll do a quick recap of some papers that we looked at last time. Uh, I think maybe a lot of the fun part of this course is looking at such papers. Uh, you will see that the authors of these papers are not having any major scientific knowledge. Um, just hold on. But they took some basic idea and they leveraged it in a very smart manner. So hopefully we will get to do some such reviews as we progress along the semester. Uh, just hold on. Okay, sorry for the interruption. So let us start. So we first looked at the problem of wideband spectrum sensing, and we said that uh, there are certain scenarios of in which we have to estimate the frequency of arrival, where the incoming signal has simply very, very, very large bandwidth, and there is actually no hope of being able to satisfy the Nyquist sample rate requirement that you have been studying in Lab 1. Uh, and so, given the technology that is currently available or currently cheaply available, uh, some aliasing is going to happen. Uh, it seems like whenever there is aliasing, there is going to be signal corruption. But in fact, one paper that we looked at last time showed that it is possible to overcome the effect of aliasing, provided that we are able to have multiple parallel branches. And then we looked at one more extension of that paper, or actually two extensions of the paper. So let us do a quick summary of that. So the first paper that we looked at was the paper by Lean and Vaidyanathan. It's called Periodic Non-Uniform Sampling Method. And it says that when there are only two users which are present, uh, then the effect of aliasing can be written like a single equation, where what you get at the output of the sampling device is some signal which is represented here as y, but that is irrevocably mixed with two uh, active user signals which are present. And this n times fs is the fold over that happens because this f is confined to be within 0 to fs. And so this problem is not solvable. It's actually an underdetermined problem. There are two unknowns, x1 and x2. X for first user and this other term which is for the second user, and they are mixed up in the single observable y. But the paper said that if we can actually form another equation which is linearly independent from the first one, then we will have two observables and there will be two unknowns, and we can relate them by an invertible matrix. And the paper actually takes this idea and applies it to any number of signals that can be present. The basic idea still remains the same: to convert the output of these sub-Nyquist sampling devices into a vector which can be written as the product of an invertible matrix times the unaliased narrowband signals. So that is the entire idea about the PNS scheme. And so the equation is given as y is equal to a times x. And if a is invertible, given y, you can recover x. Okay. Then we saw that one limitation of this PNS scheme is that the locations of the center frequencies of this narrowband signals are assumed to be known. Now, in some realistic scenarios, this knowledge may not be available. It will be impractical to make this assumption. And so we looked at a paper by Mishali and Elder, and they have called their scheme multi-coset scheme. The equation remains identical. Y is equal to a times x. But one change that they make, actually two changes they make, is that they say that this locations of the center frequencies I'm going to not assume to be known. But still I'm going to be able to solve the problem provided that I take this x to be a sparse vector, meaning it's mostly filled with zeros and there are only few non-zero elements in its dimension n cross 1. Now, as the incoming signal becomes very large in the frequency occupancy, this m becomes very large compared to the, this m is the ratio of the wideband signal that is coming at the input to the receiver divided by the bandwidth of the narrowband signal. And so as the bandwidth of the narrowband signal remains the same, but there are more and more such signals that can be present, this m keeps on becoming larger. The assumption that Mishali makes is that there are only k elements which are non-zero at any given time, and there is a sparsity present in x, meaning that k is much smaller than m. So with that sparse input assumption or sparse assumption regarding the unknown signal, unaliased signal x that we intend to recover, the authors say that we do not require the knowledge of the center frequencies of these signals. And instead, we will use a compressive sensing algorithm to recover x given y. Now, this A is a matrix whose dimensions are j cross m, where j is the number of rows and m is the number of columns. And this m matches with the length of this vector x. Now, for this scheme to be practical, this j has to be much smaller than m, because remember, this m can become very, very large. And this j corresponds to the number of parallel hardware branches that are needed. Remember that in the PNS scheme, capital J is 2 because there are two hardware branches that are needed. But here, in this compressive sensing scheme, they allow J to be little bigger, but still it has to be much smaller than M, because if we allow J to approach M, then the situation becomes very complex in terms of hardware implementation. So what the author says is that we will make J to be slightly larger than K, maybe some small multiple of K in fact, maybe 2 times K or 4 times K. But because M is much larger multiple of K, this J is still going to turn out to be pretty small compared to M. And so now when we consider this matrix A, it has much larger number of columns compared to the number of rows. And such a matrix is actually not invertible. In fact, it corresponds to underdetermined set of linear equations. It's almost as if we came back to this problem here. This is a grossly underdetermined equation, which is the problem that you looked at in the last section of lab 1. Only one row and 2 columns. And obviously such a matrix cannot be inverted. Quite surprisingly, and that is where a lot of the interest in compressive sensing has come about. The typical assumption was that whenever you are dealing with underdetermined system, the solution is not possible. The promise of compressive sensing is that, well, yes, the solution is still possible provided that we assume that X is sparse. And provided that instead of using the matrix inverse, which in this case is obviously not applicable, we are willing to use a little more complicated algorithm, which actually, I mean, a lot of the work in compressive sensing then focuses on the design of such an algorithm. But Michali and Elder's paper assume that, okay, such an algorithm is available from the compressive sensing literature, and they just directly leveraged upon one such algorithm, and then they solved this problem. So this was a good way, I thought, for you to kind of appreciate the compressive sensing topic, maybe just get an initial understanding of compressive sensing topic and how this compressive sensing method has been applied to a very practical scenario, to solve a practical real world scenario. And then the third paper that we looked at actually said that we don't want to even do compressive sensing. We do not even require this X to be sparse really. But instead of that, they actually still use the same equation that was first formulated by Lean and Vaidyanathan. But then they started taking this autocorrelation matrices. They computed autocorrelation matrix of Y, and they vectorized this autocorrelation matrix, and they somehow were able to show that vector form looks like Ry is equal to Ra times Rx, where Rx is the autocorrelation sequence of the input wideband signal. And now this is a familiar linear algebraic equation. It can be solved using some pseudo-inverse type of technique. And so if you can measure R of y, then you can get R of x. And once you get R of x, you have solved the FOA problem. Okay, so this is kind of a summary of several pretty clever ideas that are present in today's literature. In terms of this frequency of arrival estimation problem. Okay, so now I'm going to actually do a little bit of I'm going to take a related topic, but not, this is not the same frequency of arrival estimation topic, but still quite relevant. Specifically, this is the one of the properties that we had looked at earlier, where we said that this autocorrelation matrix, because it has real valued eigenvalues are real, And because of that, the eigenvectors corresponding to two different eigenvalues are necessarily orthogonal. And because of that, because of the orthogonality between eigenvectors, we can actually diagonalize this correlation matrix. And so we are going to look at one or two such properties of the eigenvectors as it relates to matrix diagonalization. In some sense, this is a mathematical topic, more on the linear algebra side, but it's highly relevant for our applications. And other thing is that I find this to be a very elegant topic. The entire concept of eigenvectors and eigenanalysis is quite, it kind of goes to the root of what is happening whenever we are dealing with matrices. Even if we forget about what the applications are, it's quite pleasant, in my opinion, to kind of do a deep dive and see what is going on. In fact, when you look at any square matrix, you see just a bunch of numbers. And if that square matrix multiplies with a vector, you typically tend to think of it as just a matrix vector product. But when we start thinking of this matrix in terms of eigenvectors, when we do what is known as this EVD, eigenvector decomposition of the matrix, we actually get to the heart of the matrix. What are the powerful aspects of this matrix operation is what is revealed by this eigenanalysis. And so that is why I thought this is pretty elegant and powerful topic that we should spend a little bit time on. Basically, we have looked at some 5 properties earlier of the correlation matrices. Remember, correlation matrices are this Hermitian type of matrices. You think of them as symmetric matrix, except symmetry is in complex conjugate sense. So there is this property which actually relates to this Rayleigh quotient that we have defined in one of the earlier slides. So there is this property which says that if I have certain vector v and this Hermitian matrix, and if I do this operation v Hermitian Rxxv, and now if I want to constrain it to some constant c, then actually what I get is an ellipse in this m-dimensional space. Okay, so this equation defines an ellipse in the m-dimensional space. M is the size of this correlation matrix. And this ellipse is oriented along perpendicular axes that are the eigenvectors of Rxx, and the lengths along those perpendicular axes are given by 2 times c divided by lambda m. Okay, so this is quite an interesting property of the correlation matrix, especially the eigen decomposition of the correlation matrix, and it kind of gives us some type of visualization of this type of scalar number that we get. Remember, the Rayleigh quotient looked very much like this, except it had another term other than this. Who remembers that? What was the definition of Rayleigh quotient?
It was also divided by, in this case, it will be v Hermitian v divided by horizontal term. Sir Arushi.
Arushi, can you speak louder?
Sir, in the Rayleigh term, in the denominator, there is also a term A Hermitian A or
Correct.
Hermitian V.
So in this case, it will be V Hermitian V. So the only other uh, change that we are making is that we are assuming that this V is normalized. Suppose if V is normalized, then this becomes Rayleigh quotient because that term in the denominator, V Hermitian V, becomes 1 by definition. Okay, now it is good that Arushi spoke regarding this because recently she has been doing some mathematical analysis in which this type of terms are appearing all the time. Okay, so if you want to know the practical usefulness of this property, I think Arushi may be able to say something about it. Okay, so let us look at this property and why it has to be true. So we will start by considering some similar quantity where instead of V, I am defining a scalar in terms of a vector D. And I'm making this vector D to be unit length. And so as I said just now, this D Hermitian Rxxd is same as the Rayleigh quotient, right? Now, in order to understand what is going on, it's sometimes helpful to start with the simplest case. So what I'm going to do is I'm going to make Rxx to be an identity matrix. And I'm going to consider just a two-dimensional problem for the sake of simplicity. So when Rxx is just a diagonal identity matrix, it is easy for you to see that if I define D as D1, D2, then this scalar becomes D1 squared plus D2 squared, right? And now when I set this to a constant, what I get is the equation of a circle with radius equal to that constant. In general, I cannot take Rxx to be an identity matrix all the time, so I'll make it to be a diagonal matrix where purposefully I have kept the diagonal elements, their notations, to be kind of the type of notations that we use for eigenvalues. But anyways, I mean, it doesn't matter. I'm taking that Rxx is still a diagonal matrix, but it is not an identity. It is not the identity matrix. And in that case, if I do this scalar computation, you will quickly convince yourself that it will become similar to this, but there will be lambda 1 and lambda 2 terms sitting in front of d terms. And from your high school math, you know that if you set this equation to some constant c, and now if you let d1 and d2 vary, then you will get an ellipse in two-dimensional space, which is centered at 0. And this ellipse will have two perpendicular axes. One is called the major axis, other is called minor axis. And the length of the major axis will be determined by lambda 1, assuming that lambda 1 is greater than lambda 2. And the length of the minor axis of the ellipse will be lambda 2. Okay, so what this tells us is that in general, whenever we consider this type of scalar product, sort of the Rayleigh quotient with d unit length, then we should start thinking of this as some type of an ellipse in some high dimensional space. And more generally, if I call this d1 and d2 to be just x and y's, then this equation is nothing but ax square plus by square equal to c. And all of these terms are having maximum power of 2. X is raised to power of 2 here, y is raised to the power of 2 here. And so this is, in general, a quadratic equation. In fact, I can take any quadratic equation where x's and y's are at the most raised to the power of 2. And then I can write that equation as this vector times matrix times the same vector. in general, there will be cross product terms. So this D1 and D2 will not be always separate. There will be some other additional term which is D1 times D2, plus some other constant which maybe, let's call it lambda 3 or something. So that corresponds to a case where this Rxx is not diagonal, it is off diagonal entries which are non-zero. But still it remains as a quadratic equation. Okay, so that is the way to think about the Rayleigh quotient that we have seen earlier. And this Rayleigh quotient actually appears in many different applications. Maybe one such application we will look at soon. Okay, so now all that we do is generalize this observation by applying that property of diagonalization of a matrix. And so you recall that when Rxx is not diagonal and it is not 2 by 2, we can still actually think of Rxx as a diagonal matrix because of the Mercer's theorem that we have seen earlier, where Q matrix is the matrix of this orthonormal eigenvectors, and this delta is formed by the eigenvalues along the diagonal. Okay, so now let us just sort out the details, and we will quickly conclude that property number 6 is to be true. Now remember, in that property we have said that we are equating V Hermitian Rxxv to a constant, where Rxx in general is not diagonal. But I'm going to put I'm going to apply the Mercer's theorem and replace Rxx by this Q delta Q Hermitian. And so now I get this entire equation over here. Now the next thing that I'm going to do is I'm going to say that this Q is a matrix, is a square M cross M matrix. V is a M cross 1 vector. And so I can actually think of this Q Hermitian V itself as a vector, M cross 1 vector. And then over here, I just get Hermitian transpose of that vector. And so going back to the notation that we had earlier, that Q Hermitian V is what I'm going to call the vector D in the previous slide. So D is nothing but projection of V onto the eigenvectors, because when you do Q Hermitian V, the columns of Q, which are the eigenvectors, become the rows of Q Hermitian. And each of the row multiplies with the vector V. It's a dot product. And that dot product is actually just a projection of V onto that eigenvector. And so D vector defined in this manner can be thought of as this projection operation. And so once I do that, this quantity, this scalar quantity, I can write it as D Hermitian delta D. But this is quite similar to what we had seen on the previous slide. The only change is that M was 2 in that previous slide. Now M became any variable. It can take a value greater than 2. But the equation still remains the same as what we saw earlier. So essentially what I have done is this general term, I have cast it into a term which we can recognize as defining an ellipse, especially when I equate this to a constant C. Okay, the last step that I will still need to make is that if I consider one specific D vector whose first element is 1 and all the other elements are zeros, right? I can, because remember these are variables. I'm allowing them to vary any way they want. That is in the quadratic equation also. If it is some equation like ax square plus by square plus c equal to 0, then x and y are variables. We are keeping them to be not fixed. So because of that variability, I can obviously take d one particular value of d to be this vector. Only the first element is 1, the rest are zeros. Now, what I'm saying is that such a d vector has to be necessarily in the direction of the first eigenvector, a1. Remember, a1 is the first row of Q Hermitian. A1 Hermitian is the first row of Q Hermitian. So I'm saying that this vector 1 followed by m minus 1, 0 is pointing in the direction of a1. If I consider some other vector d2 whose second element is 1, all the others are 0, then this has to point in the direction of a2. Can anyone say why this has to be the case?
So when it gets multiplied, it will be yielding the value of only the second eigenvector a2 in the diagonal matrix, right? When it will be multiplied, it will only be multiplied with the second element of the eigenvector matrix, the diagonal matrix in between. So
no, this Q is not diagonal. This is the
for D2.
matrix of eigenvectors. And all I'm saying is that this Q Hermitian V, when that becomes equal to 1 followed by n minus 1, 0, the result that I get, I can think of this vector as being aligned to the first eigenvector. Why is that the case?
So maybe we are finding out the projection of V over the eigenvectors.
Yes.
So if at the first position only we are getting value 1 or non-zero,
Yep.
then it corresponds to the direction of that particular eigenvector.
Correct. Very true. So Divya, I think, has got it. Remember, the rows of Q Hermitian are the eigenvectors. And also recall that these eigenvectors are all perpendicular to each other. They are orthonormal. So what this is saying is that when I get zeros in the remaining m minus 1 positions, this vector V has to be perpendicular to all of these other m minus 1 eigenvectors. And when it is perpendicular to all of the m minus 1 eigenvectors, it is necessarily aligned to the first eigenvector. And that is why we are getting 1 here. So these eigenvectors are oriented in this m-dimensional space in some manner. Whenever this vector V is aligned in the direction of the first eigenvector, and in this case it is unit length, then I'm going to get this D1 which is in this form. The same way D2 I'm going to get when the corresponding V is aligned to the second eigenvector. And so now what I can say is that if I consider that all these eigenvalues are ordered, the way I have denoted eigenvalues is that the smallest eigenvalue I'm calling the mth eigenvalue, the next highest eigenvalue I'm calling m minus 1th eigenvalue, the highest eigenvalue is the one that I'm calling lambda 1. And so a1 is an eigenvector corresponding to the highest eigenvalue. A2 is similarly the second highest eigenvalue, and so on. So that is just the nomenclature to kind of keep things tidy. So if I make that nomenclature, then what I can say is that this vector C times lambda 1 times d1, where d1 was that vector on the previous slide. So C divided by lambda 1 times d1 will be this vector. It will have to be a point on the ellipse defined by this equation. Do you get this? Why this has to be the case? Remember, we have already proven that V Hermitian Rxxv equal to C can be written as this equation here. Now, we are making this d of m squared to be all zeros, except the very first d of 1. And that d of 1, I'm making it to be C divided by lambda 1. Oh, sorry, actually there should be, I made a mistake. There should be a square root of C divided by lambda 1 instead of C divided by lambda 1. So basically, first d1 is square root of C divided by lambda 1. And so in this equation over here, if I make d square of 1 equal to C divided by lambda 1, and all of the other d's to be 0, then this summation is going to be equal to C. And same way, square root of C divided by lambda m times d of m is also going to be along on this ellipse. Furthermore, because we have made lambda 1 to be the largest, we can say that this the point corresponding to this vector is the closest to the origin. And the point corresponding to this vector, because lambda m is the smallest, this point will be the farthest away from origin. So if you draw an ellipse, then its largest axis will be defined by the eigen vector corresponding to the smallest eigenvalue. And its smallest axis is going to be defined by the eigenvector corresponding to the largest eigenvalue. And then all the other points on the ellipse will be defined by this perpendicular eigenvectors. And because this is in m dimensions, this axis will be oriented in this m-dimensional coordinate system, and individual axis will be square root of C divided by lambda m. So okay, I think while writing this, I made some math errors. So that I think I will have to clean up. But the main idea is still there. Let me see, what did I write as the property itself? This part is fine. This 2 comes because we are not going from the origin to the endpoint. We are taking the diameter, so to speak, instead of the radius. So the factor of 2 is because of that. And
So
the
they should
C
be
divided
C
by
by square
lambda
root of
probably
lambda.
has to be square root of C divided by lambda m. So maybe there was some lack of proper derivation on my part. I'll go back and look at it, but otherwise, other than those math mistakes, this concludes the proof of this property number 6. Divya has a question.
So in the Rayleigh quotient equation, we say that eigenvalue lambda is equal to V Hermitian Rx6V upon norm of V square, right?
Yeah.
So here we are saying that the numerator of that equation is C, a constant. So C by lambda will correspond to norm V square, right?
C by lambda will correspond to?
Norm V square. Should I repeat again?
Norm of V square. Yeah. Okay.
So, like if we say that square root of C by lambda into D is a vector like of square root of C by lambda 1 square or something. So then can we say that there's a relation between D and norm V?
Relation between D and norm of V.
Vector D and norm V.
Relation, yeah. The relationship between the length of V and the length of D is given by this equation. See, whenever I have some vector and I take its projection on an orthonormal matrix, in general, this is also called unitary matrix. And maybe it is called unitary because it doesn't change the unit. In other words, I can take any vector and I multiply it by Q Hermitian, then I'm going to get another vector whose length is going to be same as the length of V. Okay, so this is
Okay.
it can be proven very easily. Okay, there is another problem. This D1 to dm, this rectangle should be have a transpose term as a superscript. So this is a tall vector. It is not a flat vector the way it is shown here. So the length of this vector D should be D Hermitian D. It's squared length of D. Right?
Okay.
When I do D Hermitian D, I get summation of D1 squared plus D2 squared plus all the way up to dm of squared. And that is just the squared length of D. If I do D Hermitian D, then this becomes V Hermitian Q Hermitian V.
Yes.
But the in between term Q Hermitian is an identity matrix because Q is an orthonormal matrix.
Okay.
And so D Hermitian D will be necessarily equal to V Hermitian V.
V Hermitian V.
So that I can say even regardless of this other part, just by invoking the orthonormality of the matrix Q.
Okay.
Joel, did you have any question?
Yes, sir. I was just saying that instead of under root C by lambda, we should have C by under root of lambda m.
Yeah. You are right. I think so. Yeah, it is just my little slopey math here. So please bear with me. But I know you all are more than capable to correct the slopiness of this math here. But anyways, the main idea that I would like you to take away from this is that this matrix operation, especially when we are considering this type of Rayleigh products, it really tells us how the matrix is going to behave. In more specificity, we would like this ellipse to be more like a circle rather than like a really long, thin ellipse. Whenever this ellipse is like a circle, the a lot of these signal processing algorithms work better. But when it starts becoming like an ellipse, especially elongated ellipse, especially where this smallest eigenvalue is much larger, much smaller than the largest eigenvalue. So lambda 1 is much, much bigger than lambda m. Then what I will get is the ellipse will start becoming like a line, because the minor axis will be much, much smaller than the major axis. And it is in this type of situations that sometimes these adaptive algorithms start exhibiting problems. Okay, so that is that. Now I want to mention one other property. I think this property we will be making use of later on in this course. The property 6 is useful for us. The last property that I'm going to talk about today, yes, Bhavesh?
Sir, throughout this derivation, when we are considering it as an ellipse, it is basically when we are having only two variables, right? I mean, in the whole derivation, that m that has a velocity of 2, or if it
In this case, m
increases,
is 2.
yeah. So if it increases, then it will no longer be an ellipse, right? It will be more staggered in other dimensions, right?
Right. I mean, see, what our brains can visualize is an ellipse only in 2 dimensions. That's why
Right.
I considered this case. But mathematically, it still remains ellipse. Even when m becomes 10,
Yeah, in that
mathematically it is
dimension.
still an ellipse. If you can somehow visualize the 2-dimensional ellipses that we are familiar with, if you can think of them as occupying an m-dimensional space, then that is what we get. So not the type of ellipses that we are used to seeing, which is this 2 by 2 case, but mathematically this is still an ellipse. This equation over here, you can think of it as a mathematical ellipse in this m-dimensional space.
Yeah. Okay.
In just the same way that we can visualize a circle in 2 dimensions, but if all these lambda m's are same, then when I set this to a constant, I still get a circle, but that circle is some strange circle in a high dimensional space. All the points along the circle are at the same distance from the origin, which is the definition of a circle. Okay. So now the last property that I'm going to look at, as I said, I don't know when we will be applying, or if at all we will be applying this property, but it is still quite a relevant property, which is that if I take this matrix R, and if I keep on multiplying that matrix with itself, then the resultant Rxx to the power n has exactly the same eigenvectors as the original Rxx. And the eigenvalues become the original eigenvalues raised to the power n. Yes, Bhavesh?
Sorry, sir. That went by mistake. I thought it was still up, so I just
Okay,
pressed the
sure, no problem. Okay, so this is another property of a matrix. In this case, this Rxx uh, uh, just getting multiplied with itself a number of times, and the resultant matrix ends up having the same eigenvectors and the eigenvalues which are nth power of the original eigenvalues. This property is mathematically pretty easy to prove. I'm going to just prove it for the base case, and then it can be proven by applying the principle of induction. So what I'm going to do is I'm going to take Rxx and raise it to the second power. So this Q delta Q Hermitian I'm going to multiply with itself. But remember, this Q Hermitian Q is identity, and so I get Q delta square Q Hermitian. But this looks just like the original equation where delta became delta square. And so we can say that Rxx to the power 2 has the same eigenvectors. The eigenvalues became the square of the original eigenvalues. And if I repeat this process multiple times, then I get this statement of the property. The reason I'm bringing it here is because this is a pretty powerful property. It again exhibits the heart of this matrix. It shows what this matrix is really doing, especially if you consider repeated applications of this matrix. And so let us consider one last property in which again I ordered this eigenvalues in this manner. Given property 7, what I can say is that if I keep on doing this repeated multiplication of Rxx with itself, at the end, what I'm going to end up with is just the first eigenvector and the eigenvalue corresponding to that first eigenvector raised to the power n. So it's as if this matrix converges to this eigenvector. All of the other eigenvectors go. Basically, the matrix ends up being just one rank 1 matrix. Essentially, all of the power of the matrix gets pretty much concentrated along the eigenvector corresponding to the first eigenvalue. And this is the proof of this property. So this equation we have seen earlier from the Mercer's theorem. Remember, the eigenvectors are remaining the same. The eigenvalues became raised to the power n. So this equation, obviously, I can write it as this second line. Okay, I think I made a mistake here. And this mistake I had noticed yesterday. I thought I corrected it, but apparently not. Sorry about that. Let me see if I can find my corrected, edited version. Then I'll just show it to you. This is not going to do it. Okay, so I don't have that corrected, edited version, so please bear with me. What I can tell you is that make all of this less than or equal to sign, just flip it. Okay, so lambda m becomes the highest eigenvalue and lambda 1 is the smallest eigenvalue. So that was the typing mistake that I did. Actually, I want to continue with this, and this lambda m I would have to replace with lambda 1 and so on. But instead of that, I'm going to say that lambda m is the highest eigenvalue, lambda 1 is the smallest eigenvalue, and so all of these less than signs have to be flipped. And now this property will say that because lambda m is the highest eigenvalue, limit value of Rxx raised to the power n will be lambda of capital M raised to the power n am Hermitian. Okay, so that becomes the statement of the property. And we will see why that property has to be true. Now remember, lambda m is the highest eigenvalue. am is the eigenvector corresponding to that. So I'm going to write this equation in this manner shown in the second line, where I took out lambda of m to the power n outside of the bracket. And so the last term becomes just am Hermitian. And the remaining m minus 1 terms are the same as this, except all of this lambda m's I have to divide by lambda of capital M. Now, because I'm saying that lambda of capital M is the highest, this ratio obviously has to be less than 1. Lambda of small m divided by lambda of capital M is some number less than 1. And if there is a number which is less than 1, if I raise it to the nth power, it becomes small. And in the limit n tends to infinity, it becomes 0. And so this Rxx to the power n becomes just this quantity over here. Okay, so this is kind of, maybe I should have called it 7.a. It is sort of an extension of this property. Now, this is also a very powerful property. It has many applications. So one application is in some iterative algorithms where there is some vector x and it gets modified by the same matrix R, and you get the next iteration. Then that new vector of x gets again multiplied by R, and you get the new x. So k is the iteration index, and within the iteration, what is happening, we can kind of simply formulate like this. Natick, I don't think is here right now, but if you want to see an example of iterative algorithm where this is happening, just talk to Natick. In fact, we didn't even know that we were doing it. We were doing this type of mathematics, and Natick figured it out that the algorithm that we were working on, its essential operation inside the loop can be written like this. Okay, so this kind of came to us. We didn't go searching for it. So it kind of tells you that this may not be that uncommon. We stumbled across it, but in some other cases, this may be happening also. Arushi also knows about this. So because of this particular nature of our iterative algorithm, we could directly apply this property, and we could say what this iterative algorithm is going to do as n becomes large. And actually, we found out that this n doesn't have to be infinity. It doesn't have to be even large. Even after 2 or 3 iterations, when n is maybe 3 or 4 only, we pretty much ended up getting this equation. And so now I can predict ahead of time what this iterative algorithm is going to do, because I can do the eigen decomposition of this R. In fact, it doesn't matter what x is. Okay, and this is a statement that I'm going to let you figure out on your own. What this property says is that irrespective of how I initialize the algorithm, no matter what x of 0 is, at the start k is equal to 0, so I can make x to be anything. The final answer is going to be always this eigenvector a1 multiplied by a scalar. Okay, so did you get what I said? Whenever this equation can be applied inside an iterative algorithm, what I'm saying is that it doesn't matter what x of 0 is, how I initialize the algorithm. The algorithm is always going to tell me the final vector x is going to be a1, the eigenvector corresponding to the largest eigenvalue. Or I think with all these typos, it will be a of capital M. except that A1 or A of m will get scaled by some scalar. That scalar will be a product of lambda 1 raised to the power n times something else. So this property can allow me to analyze the operation of the algorithm, and it can actually allow me to make a very definitive statement that how the algorithm is going to converge. So that is something that I will ask you to figure it out on your own. But it's not just the algorithms that benefit by this property. There are these continuous time differential equations, which you may have seen in your high school physics course. These equations actually describe simple harmonic motion, for example. They also describe the operation of a constrained spring, when that spring is either stretched or compressed. And then you let go of that force that you are applying on that spring, and the spring starts oscillating. In a lot of these cases, especially where there is coupling between different parameters, these differential equations can be written in a matrix form like this. Now here you will see that this dxt divided by dt takes the form of xk plus 1, a takes the form of r, and x of t takes the form of xk. So in a lot of physical systems, something like this is going on. And what this property says is that the solutions that are going to survive are going to be dictated by this eigen analysis of this matrix. And it turns out that in a lot of the cases, the solutions are e to the power lambda some element of a times t. And that actually ends up being our complex exponentials in some specific solutions. And so that is why we get this oscillatory behavior, sinusoidals, cosines and sines, which come out of the solution of the simple harmonic motions and more complicated harmonic motions. This property is applicable in the wider world also. And then, if you are still not convinced, I'll tell you one other reason why this eigenvalue decomposition is highly useful. Just maybe 20 years or so back, one of the founders of Google actually leveraged this property. And he came up with an algorithm. He called it PageRank algorithm because his name is Larry Page. And so Google's underlying algorithm was called PageRank algorithm. And it also made use of this type of property, I think. I know for sure that it made use of some eigen decomposition of the, basically what Larry Page did was he converted the interconnections between different web pages. He converted those into a graph, mathematical graph. A mathematical graph can be cast as a matrix. And it is that matrix that he did eigen decomposition of. And that is how we figured out the web page to go to, probably by looking at the eigenvalue corresponding to the largest eigenvector. So this property is that way pretty powerful property. Okay, so I will take a break here. I think we are about 1 hour into the lecture. We will spend another 15-20 minutes, and then we will conclude for today.